Today I want to talk about the project I built for observing the stars from a city. So a common problem when you try to do stargazing from a city is that a lot of the horizon is obstructed by buildings around you, maybe by, the area is not flat and things like that. So it's very hard to know with certainty what you can see in the sky, especially if something is very, if it's like a planet or a sky you're trying to look at is relatively low altitude. So let's look at first. Let's look at the result of how it would look like to get you motivated to watch the rest of the video. So here, as you can see, the map of the area, and you can see the direction of where each star is visible. And at the same time, you can also, additionally, what you can do is you can plot the star names and plot the timeline of where you can observe, or when is the time that you can observe these stars. And besides the timeline and the map of where to look, what you also want to know is things like altitude and azimuth, so the direction and the angle at the sky at which you can see this object. So you can do this for multiple locations within like a same area. The thing I want to call out that the method I will describe here mainly works for a certain small area. Mainly because we have to make assumptions about the heights of buildings, or we have to get that data. So that's why it's difficult to cover large areas with this. But I assume for most practical users that you would be looking from the place you likely know. So yeah, you can do this for multiple locations. That's the beauty of this method, that anywhere, any point within the region that you know, you can basically calculate the direction where something will be visible, the time when it will be visible, and also the altitude. So let's get started. I want to walk you through. I want you to walk you through two ways of getting this done. First, let's consider a relatively simple way, where you essentially use a compass to figure out the direction you're looking at. And the second method, that is a little bit more complex, involves taking into account the elevation, the heights of buildings, and you get a more realistic view of what can be seen in the sky. Let's start with a simple approach first. We're going to use a compass to determine the direction we are looking at, and together with our altitude, we can estimate the horizon we are seeing. So let's look at that. Here's our Jupyter notebook. Basically, we can see what we are doing here is we are taking the image. That's the image taken from outside of my window. Basically, we are looking at the GPS information for latitude and longitude, and we are looking at the besides that, the image data also, the EXIF data contains your elevation, the height above ground. And so with a simple formula, we can calculate the distance to the horizon that we can see, given this elevation on the perfect sphere. And once we know that, we can plot those points within this range on the map. So we plot this, and here how it looks like, and you can see right away that the things that become very apparent is that how different it is from what you are actually seeing. So the obviously you're not living on the surface of a perfect sphere, so your horizon will be typically closer to you. And okay, so this is a start, and I think the beauty of this method is that this is a simplification, obviously, but it's a reasonable thing to do as a first try. And it works. This imperfect estimation works surprisingly well for the initial version of what we can see in the sky. And let's get started. So we are gonna use the Skyfield library to do the heavy lifting for us of calculating planet and star positions at a given time. But before you can use the library, we need to do a setup. We need to define our location. We need to define the altitude, the height above the ground, the bearing, the compass, meaning the compass direction, and time zone. And just to be clear, so we use the compass, but actually you can use an Android app to measure the direction equally well. One thing that I wouldn't trust is the compass direction that's logged inside the EXIF image on the photograph, because that tends to be not very accurate. So we set here's how we do this in Skyfield. We set our location, we set altitude. So after we set the location, we need to set the time. I mean, generally, the stars become visible after the sunset and before the sunrise. Of course, depending on your location, depending on the cloud cover and whether you're actually awake to see them. Luckily, there is a library, Astral Python library, that can tell you the sunset and sunrise location, sunset and sunrise times at a given location. What we also do, we'll define a function two functions to check that the planet is within our field of view, meaning between the two bearings which we measured with compass, so we roughly know what's the angle we can see, and we also check whether it is above the horizon. So very 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 simple check. After that, what we do is we simply iterate over all the planets and get the time of the sunset. And while we're in the specific time range, so we want to limit this, for example, to the current day only, we check the planet if visible. If it is, we save the time in the local time zone, we save its altitude, azimuth, direction, and we're looking at, increment the time, and continue. So end result, you have this dictionary of planets visible at a certain location within your field of view. And plus, you have the event times of the day. So the rest is essentially plotting these positions and times. So typical altitude azimuth plot is very useful for you to imagine where you could see the planet. You would also like to plot a kind of calendar or the date or the times when each planet becomes visible. And you can do the same, by the way, for the stars. So it is very similar process to the planets, except that now we are going to use this Hipparcos data set for the star locations, and we are going to filter. We're going to limit ourselves to only very bright stars, so magnitude 1 and below. Let's assume that we are living in a very light polluted city, so it's very unlikely we will see dim stars. And a similar principle as for planets. We basically iterate over them, and we plot the altitude, azimuth, and we plot the schedule of when we can see them. So far so good. This is our simple approach of knowing what stars and what planets are visible above the horizon at a given time, and it works. The disadvantage of this is that we are now focused on a single location where we have to use compass, and we have to estimate the field of view. We have to estimate the direction which is of the sky, which is visible to us, and this is not perfect. First of all, it narrows. First of all, it limits us to only like a handful of points where we know this metrics. And so we would like to, we'd like to, scale it up. And another point is that, yes, this is right now this is a view from the window, but typically when you observe the stars, you are not at your home; you're actually outside, and you happen to see the dark sky that allows you to see something in it. And so over time, as you get to know the area you live in, you notice those places where the sky is dark enough for you to see the stars. So the places that have minimal light pollution and relatively unobstructed view of the sky. So as you learn to see those places, this becomes a place where you typically would expect to see something. and then you would like to use the approach that we have worked just now to this more general problem. And as I mentioned before, the most common problem is typically the buildings that are blocking your view. And another issue with it is that even you know that at a certain location there is a building and it prevents you from seeing things, it's difficult to judge from the ground level to what extent or what's the angle of the view that's blocked each building. And so basically by knowing the locations of where are the ideal stargazing spots in the area we stay in, and knowing the buildings and polygons, building polygons based on the OSM maps and the heights of the buildings, we can work out what is the angle of the sky that's visible to us. And this is very useful because with that you can see, you can know what are the things that are visible to you from this location, and not only what is visible to you now, but importantly you can start to make forecasts, like what will be visible next week, what will be visible several months from now. Actually, there's no limit to the amount of predictions you can do. So, I mean, first let's start with the building polygons. I mean, we're going to use the OSM maps, OpenStreetMaps, that is. Not all buildings exist on the OpenStreetMaps, but the majority of the bigger buildings do. And to compensate for the fact that some are missing, we're just going to add a few placeholders to the other areas. I mean, the assumption we're making here is that you are interested in knowing what can be seen from a specific location, so a specific area, and mainly we do that because we want to reduce the file size we're working with. But technically, you can of course scale to bigger areas as well, should you want to. So first thing we're gonna do is we're gonna take the OpenStreet data, and we are gonna we're going to, because it contains a lot of data, roads, parks, trees, things like that. So most of the things that we're not necessarily interested in this case. So we're gonna do a couple of do a few filters on that data. So importantly, and we'll get very specific. We'll get, assuming we have a like finite number of buildings and the area is relatively small, we can actually go ahead and specify that these are the building IDs, these are the way IDs that represent the buildings we're interested in. And so we're going to filter on that, and finally, once we have that OSM file, we are going to process it with a simple Python script. And the purpose of it is really convert the OSM file into CSV, which is a lot easier to work with for us. So now what we're going to do, we'll download the data GeoTIFF file from Open Buildings dataset of Google, and we're going to use the area of the polygons which we got from with OpenStreetMap to get the mean height of that building from the Google dataset. Yeah, that will effectively, and that we will store as a result as another CSV file, which basically contains the building, the polygon, and the height. We know the azimuth, this is direction where the star is visible. So for the purposes of knowing whether that star is visible, we need to draw a line between that star and ourselves. So to draw a line on a sphere, and we're gonna limit this line to the ideal distance that you can see from the height, like average person height 1.7 meters. So you can see on this perfect sphere, you can see 4.6 kilometers away, and so we're going to draw a line from our location, which is our stargazing location, to in the direction where we can spot the star, and that line will be 4.6 kilometers long. So this, what this tells us is, what this enables us to do is that we want to find any place where this line intersects any of the buildings. So then we um, then we know whether there's something blocking at the path, and if there is, then we would use the building height and our distance to the building to figure out whether, given the altitude or star, whether it's still visible. Now what we're going to do, we're going to iterate over all the locations, basically latitude, longitude that we have defined, and we are going to, inside that, we're going to iterate over all the stars, and for each star at each time, and we're obviously going to increment the time each hour or any granularity you want. You're going to iterate over that and check, and basically log the altitude, check whether the star is above the horizon. That's the first check, and if it is it obstructed by buildings? And the way, so maybe worth explaining a little bit how we determine the angle given the okay, let's assume that we have found a place that the line we draw between our location and the star intersects the building. So next thing we want to know the point of that intersection, one, so we can calculate the distance from our location to that point, and secondly, we want to know the height of that polygon which got intersected. And once we know the height of the building and the distance to it, we use simple trigonometry to figure out the angle which gets formed. We assume this is like a right triangle, and we figure out the angle of the hypotenuse, basically connecting our location to the star. And that will be the angle that is a minimal altitude in degrees that the star becomes visible. And once we collect this data, we can do a few plots. Mainly, we can draw our location. We can draw a star location on the map, top-down view, and we can say that in this location this star becomes visible. This location, this star. So that's a simple visualization. Then we of course want to make, just like with the planets, we want to make a timetable. So we know we intentionally restrict to a certain time of the day and night that the stars become visible, and so we can be sure that we are able to observe it. And finally, we want to plot the altitude and azimuth of each star, and we want to know that where in the sky to look for it. And that's about it. I hope you enjoyed this tutorial. I highly recommend you go and try this for your own location, and don't worry if you don't have a data set for the building heights. You can always do approximation, which is for the heights of the buildings, using an OpenStreet data. It won't be as accurate, but it will be fairly good. It will be probably good enough for most of the cases. Thank you for watching.